Alright, first of all, thanks everyone for coming, and this will be our first event for this week's workshop. And for the schedule for tonight, we're starting now, and then I'm going to give you an introduction to quantum computing, and I'm going to go until about 7, but maybe I'll be done a little bit before then, and we'll try to have some questions. And then Professor Chu is going to come and do some intro to linear algebra and Dirac notation at 7. That should take about a half an hour, maybe 40 minutes. If you have to leave, we understand. This will all be recorded, so you can come back to it. And then the rest of the week, we'll post the schedule. But tomorrow is going to start at 5:30 p.m. in the Foldy room. And we're going to start with Professor Berezovsky. He's going to do an intro to quantum mechanics, and he's going to talk a little bit about. I don't know if he's going to talk too much about logic gates, but he's going to talk about like quantum measurement and entanglement and superposition. But you don't need to know what that means yet. And then after that, Adrian is going to give you an intro to Qiskit, and that'll be tomorrow. And that might be a little bit longer day as well, maybe just an hour and a half, maybe tops. And then the rest of the week should be shorter days. We're working out a time for Wednesday, and then Thursday, JP Morgan. What did she talk about? Morgan Stanley. 5:30 p.m. tomorrow. No, 5:15. My bad. 5:15 tomorrow. And then that'll be about an hour and a half. And then Wednesday, we're working on a time. And then Morgan Stanley has someone who works on Qiskit finance, and she's going to be giving us a presentation on Thursday. But that's going to be over Zoom at 7:30 p.m. at night. So we won't meet in person that day, and you'll be able to ask her direct questions. And then Friday, we're also working on a time. We'll do quantum machine learning. I think that's all I have for announcements. I'll try to post another schedule in the Discord soon after this meeting for the next couple days. And if you have questions, use the Discord. And so we'll get started. I'm going to play you an introductory video now, so I don't have to worry about it later. Has anyone here registered for the hackathon? Has anyone here not registered? So we have a poster here for you to scan. Okay, so. As you know, we're partnered with IBM Quantum and Qiskit for this. So Brian is one of the representatives that we've worked with, and he recorded a welcome video for everyone that I'll play today.
Hello, and welcome to the Qiskit Fall Fest. My name is Brian Ingmanson, and I'm the Education Engagement Lead at IBM Quantum. On behalf of IBM and the entire Qiskit community, whether you're online or in person, thanks for being here. The Fall Fest is the biggest student-led event for quantum computing in the world and continues to get bigger. This year we have more than 2,500 participants worldwide, spread across 29 different Fall Fest locations. There are 120 student leaders who have dedicated their time and energy over these last months to organizing each of these events, including the one that you're at today. Now, I can't be in 29 different places at once, which is why you're seeing a recording of me. But trust me, this energy is real. I am so pumped for you to be part of the Qiskit Fall Fest. You will be participating in a series of events that your student leaders have planned exactly for you. Each Fall Fest is different, after all, and designed specifically for the campus it's happening on. For some of you, this may be the first time you've ever explored quantum computing. The word entanglement might just mean a messy relationship to you. For others, you might be pursuing a PhD or a graduate degree in the field already. We believe the Fall Fest is for everyone and can lead you to a brighter future. I wanted to take a moment to highlight 2 opportunities. First is the IBM Quantum Internship Program. Applications are open right now for the summer of 2023. Our internship program is one of the best in the industry, putting you directly on the teams that build the hardware, program the software, and research the future of our field. From working on error correction to writing chapters in the Qiskit textbook, our interns make real contributions across the entire stack. This past year, our interns even organized a fireside chat with the Quantum VP, Jay Gambetta. The second opportunity to highlight is the Qiskit Advocate Program. This is a global program that provides support to the individuals who actively contribute to the Qiskit community. The advocates are the top-tier members of the Qiskit community who have the chance to work directly alongside IBMers through a mentorship program and get exclusive opportunities for networking. Applications to join the Qiskit advocates typically open once per year in the summer. And a fun fact, almost every student organizer in the Fall Fest is either a current Qiskit advocate or a former IBM Quantum intern. That's how we know you're in good hands for this event. For more info on both of these opportunities, follow Qiskit on Twitter or IBM Quantum on LinkedIn. Okay, thank you again for joining us. We are so excited for you to be here and take the next step on your path. Please dive in, challenge yourself, learn more about the community, and have fun. I've been Brian Ingmanson for IBM Quantum. Have a great day.
Is he actually above?
He's trying.
So he said, I'm calling for the most monitoring
All right, let's get started. I'm going to sit down. I don't feel like balancing on one leg or crutches for the whole presentation. I apologize. Before we talk about quantum computing, let's talk about chess. So there's a classic fable about the inventor of chess, and he made this great game, and he talked to the emperor of wherever he was from. And he says, "Look at my amazing game." And the emperor goes, "Wow, what should I give you as a reward?" And the chess player goes, he thinks about it for a minute, and he goes, "Just rice, your highness. Give me 1 grain of rice, and then the next day double it, and continue this for all 64 days per 64 squares on the chessboard." And the emperor is like, "Well, that's such a modest request, of course." He's thinking, well, rice is nothing. And so for the first day, the inventor goes home with a single grain of rice. But then 7 days in, he has 127 grains of rice, almost a small snack. But by the time we have 30 days surpassed, because of the power of exponential growth, the inventor has over 260,000 full bags of rice, starting to get somewhere. But then 64 days in, he has a mountain of rice. So you can see, even with small grains of rice, the power of exponents are immense. So after giving you a nice attention getter via Brian, he gives you a great idea. We'll talk to you about quantum computing, and Brian also helped with the slideshow. Our first point we want to talk about today is that anyone can learn quantum. Anyone can learn about quantum computing or quantum mechanics or any of it. It's really not that complicated. A lot of people think that, oh, this is some unattainable subject, but it's really not. And both the story of quantum computing and that chess story share principles. And a lot of the problems begin very simple, but as you scale them up, they get very complex and need a lot of help. So the Qiskit community believes that anyone can learn about quantum computing, and they're there for you along your journey. So we're going to talk a little bit more about the scale of quantum computing, and I'm going to give you another example, but this one's a little bit smaller in number, I guess. So a question for you all is, how many ways can I arrange a dinner party of 10 people where the order of where they're sitting and who you're sitting to matters? Exactly. So you do 10 factorial, which would be 10 times 9 times 8 and so on, which is just over 3 million options. So every time you add one more person to the party, the problem grows exponentially. So this very quickly gets out of hand. So if you were to think of like 11 more people, you multiply that by 11 and so on. So you can realize as this problem scales, you get into huge numbers. But when you try to think about this problem, 10 people at the dinner party seems like a pretty simple problem. Our computer could probably handle modeling that, and you would be right. But let's think about some other problems that would be more complex than just 10 people sitting at a dinner party, and you could see why maybe our computers are running into a bit of an issue. But you may be thinking, but don't we already have really powerful computers that can easily handle big problems? And you're correct. We do have really big computers, and they do handle really big problems. And an example of that is the IBM Summit supercomputer. Now, the IBM Summit supercomputer has 9,000 IBM Power 9 CPUs and 27,000 NVIDIA GPUs, and it's used to simulate or simulate viruses, predict weather patterns and natural disasters, and help scientists around the world with their research. So that's 250 petabytes of memory, which is like if I strapped together 2 million iPhones. Now you're thinking that's a lot of storage. What could possibly use this much storage? Well, this model, with all of that memory, can still not predict something as simple as caffeine. Now, caffeine, hold on, let me start over here. Caffeine is, as you can see on the screen, the molecular compound of caffeine. And even IBM Summit supercomputer is not powerful enough to simulate a caffeine molecule in perfect fidelity, with understanding of how every bond and electron force interacts on one another. So there are classical methods that can efficiently approximate about the caffeine molecule today. But if you wanted to represent a caffeine molecule at a single instant with complete fidelity, that would take approximately 10 to the power of 48 bits. This is far more than even Summit can handle. Summit can handle 10 to the power of 16 bits. That's a huge difference. And this is something as simple as caffeine. Yet caffeine exists. Nature has found a way to understand the easiest way to arrange those electrons instantly. Nature is an unbelievably powerful calculator. And it turns out, this is foreshadowing, nature didn't have to ask a computer how caffeine molecule should be shaped and how the electron should interact. It just makes it happen. Even though those decisions are so small and hard to simulate, our computers cannot. So some problems are too small to be seen clearly. The duality of big and small is exactly where quantum lives. This is when we talk about quantum mechanics. We're really describing the laws of nature at a really small scale. Things like atoms and electrons. Very small things just behave differently than what humans are used to seeing every day. So a lot of times when you're learning quantum mechanics, it's just hard to wrap your brain around it because when you go to such a small level, it's not something you're used to seeing in everyday life. Like in physics 1, you're talking about a ball on a ramp. You could go outside and drop a ball down a ramp and kind of see what's going on. Let's see. Yeah, that's all we got here. So, quantum computing. We harness the laws of nature to tackle these hard problems. And why quantum matters. Even though quantum computers are very limited in many different ways right now, the potential remains huge, and we can create a new paradigm in how we solve problems. Quantum computing provides us new algorithms, new approaches to problems, and new technological breakthroughs, and all thanks to qubits. Now, what is a qubit and why is it special? First, a simple breakdown of a qubit. The name comes from the description of a quantum bit of data. And qubits have special properties, and we'll explore these a little bit now, and I believe Professor Berezovsky will expand more on them tomorrow. Now, there's a few different ways to physically make a qubit, and also a qubit, you can think of it similar to a bridge, and they can be constructed differently with varying strengths and weaknesses, but they all serve the same purpose, and that's computing. Now, a classical bit is really just considered as a 1 or a 0, but we'll talk here in a moment about some of the special features that qubits have. We'll talk first about the main one, which would be superposition. Now, here I have an example of a way you can think about superposition. And so we're going to think about some pennies. So imagine you have 3 pennies and they're all sitting on a table. They can only be in one state at a time, heads or tails, and you can measure this state. So when you look at all 3 pennies, they can only be in one unique order at a given time. And this is how computers work. You can think of those states as ones or zeros, however you want. And for n pennies, this problem scales as n to the power of 2 possible states. So for 8 pennies, we have 64 states. Now, let's think about some quantum pennies. So in the world of quantum mechanics, we can spin these pennies. And we're basically going to say, like you can even think of it as flipping a coin or spinning the coin. And when the coin's flipping or when the coin's spinning, we don't know what it is. We don't know if it's a 1 or a 0. We're going to say it's a superposition of both of the positions. And this gives each penny a 50% chance that is in a state that will be heads and 50% for tails. And so we're going to call this superposition, and it allows us to work with far more states at once. It provides an exponential speedup. So now for n pennies, we have 2 to the n states. So for those same 8 pennies, we now have 256 states. Every time you add one qubit, the total number of possible states doubles, same as the dinner problem. So now we can see here how we're using those laws of nature to our benefit. And superposition allows us to look at some really big problems like chemistry simulations and optimization problems in much more efficient ways. And some of these ways are going to be what you can explore this week and next week in your projects. Now, the second property of quantum mechanics, and specifically being applied to qubits today, is entanglement. Now, this is kind of where some people would say this gets weird. The people who think this is weird include Albert Einstein, who described it as spooky action at a distance. Now, it's hard for us to have a classical understanding to explain what happens here, because, again, like I said earlier, we don't have anything in our everyday life that simulates entanglement. Now, essentially, two qubits that are entangled become correlated. Even after those qubits have been separated, when you observe the one, you learn something about the other, no matter how far away they are. So if you have your two entangled pennies, move them to the opposite ends of the room, you measure one, you know something about the other. Now that's weird to think about. For our understanding, it's only important to know that the qubits in quantum computers can become entangled, and that allows researchers to set up problems in a very different way. And the more you learn about quantum mechanics, the farther you can delve deep into like why that happens and what exactly is happening. Now, here's basically a summary of the last few things we just talked about. Quantum computers use special bits of data called qubits, and that's an important term to remember. And they follow the law of quantum mechanics. And we use these laws to our advantage, enabling us to put qubits in superposition or to create entanglement. Now, using these techniques, quantum computers can harness nature to compute problems that are too large for classical computers to solve. Now I'm going to talk a little bit about what does a quantum computer look like and what would the hardware of a quantum computer be. You don't really have to worry about this too much directly in like your projects this week. We'll be doing all of Qiskit and some coding, but this will be nice for you to know. Now here is the IBM System 1. This is a state-of-the-art quantum computer developed by IBM in 2019. The computer is inside this big shiny cylinder. Even though it looks futuristic, each part of this is necessary for the quantum computer to work. The shiny cylinder is actually a dilution refrigerator, which keeps all the components cooled to the right temperature, and it shields them from interference. Inside the shiny cylinder is what we call the chandelier, which is composed of electronics, wiring, and protective elements which allow the quantum computer to function and take commands. And here you can kind of see a classical schematic of what the chandelier looks like, and this is a pretty popular clip art you may have seen before if you've looked into quantum computing. Now here's a picture of an actual chandelier, and at the very bottom of the chandelier is the actual quantum processing chip, which is about the size of a stamp. On this chip is where all the qubits live, where all the calculations occur, and where all the quantum magic takes place. And you can think of them almost like a normal CPU for a normal computer in terms of like size and what those look like, except these ones are special and have a giant chandelier and box cooling them around it. Qubits are also very fragile, and they don't like to be annoyed by things like air or light. And scientists have to build a container that would keep all of those factors away from the qubits, hence the giant container. And those cables are the microwave coaxial cables that send and receive information from the qubits. So we're going to use microwaves to send this information from the qubits. The white cylinders are other devices either being built or operated behind the scenes. And the feature layers of shielding that protect the quantum processor from any radiation. We use an electronics rack, which isn't shown here, that sends signals in and out via the microwave pulses. And we'll talk more about this process in a moment. I even will have an animation that will help make this process make sense. So next, we'll talk about the processing chip. So here we're going to zoom in, and you can see the different parts of the chip itself. The dark blue squares are the qubits, are quantum pennies, as we just talked about. The squiggly lines are microwave resonators, which is how the pennies talk to each other, and the computer sending it instructions. Now, to work properly, this needs to be cold, colder than outer space. You have to get almost to 0 degrees Kelvin, so that's really cold. And then, well, I'll show you a diagram here in a minute, but something I do want to point out that I've talked to a couple people about, especially some CS people have asked me like, okay, so what happens with like quantum computers? How are they just going to replace normal computers if like you're sending microwave pulses, and how do you read that? Well, you pair it with a classical computer. It's not completely taking over what a classical computer would do. To take a moment, an analogy that I was once told was you could think of a classical computer like a light bulb and a quantum computer like a laser, where a laser is much more powerful than a light bulb and it can do specific tasks really well. But you're not going to have a laser in every house like you have a light bulb in every house. So the light bulb may have more broad tasks, but the laser can be used, especially in research, for very specific things. So that's one way right now you can think about quantum computers versus classical computers. So you're not really throwing your current computer out the window just yet. So what we do is, because, as I talked about, quantum mechanics, you can describe it as a little bit weird, and some of that data isn't binary, how like normal computers are used to reading it and how we're used to reading it is, we directly hook it up to a normal computer. So here's a schematic, or here's a quick animation of what's going on. I'm gonna let it play through once, and then I'll explain it. So you can see we have that laptop there hooked up to this big quantum computer. You can see some stuff's going on. It's getting to the chandelier, and it's gonna come back. There's the little quantum processing chip we just talked about. Microwave pulses. And we're back to binary. So I'll explain this process one more time, and then we'll go through the animation again. See if I can pause this. Okay. So here's how we actually use the quantum computer. From your laptop, you can write a set of instructions, which we'll call a circuit, for the quantum device to run. So those instructions arrive at a large computer rack connected to the quantum computer. So the giant encapsulation of that chandelier. And that takes your instructions and translate them into a microwave pulse. That microwave travels down the chandelier and arrives at the qubits, which interpret those pulses as commands and perform the operations you asked for. The qubits send pulses back up the chandelier, which are translated back into binary code, which we can use. And then it's sent instantly back to your laptop, and this whole process takes place in a matter of seconds. So let's play this one more time. Maybe. All right. So your computer, your circuit with your instructions, you're going to send it. It's going to go to the computer rack. It's going to take your code and put it into microwave pulses. You're going to send that down the chandelier to your qubits. And now you're going to send those microwave pulses, and that's how the qubits can read them. The qubits will do their thing and analyze it or whatever you told it to do. And it's going to send it back to the rack. It's going to change it back to binary right there. And then boom, you get some binary code on your computer, which you can use or read or interpret, whatever you need. So that was basically everything I for sure wanted to cover to you. Professor Chu will be here at 7, so we have 13 more minutes. I have a couple more things we could talk about, but also we could take a minute here. Do you guys have any questions? Does that anything not make sense? Questions? Get attacked by a bug over there? Yeah. All right. Let me take a look here. We'll briefly skim through some of these other slides that I have prepared. Brian had a few more topics to talk about. I don't want to put too much on you guys, but we'll talk about a couple of cases which quantum computers are used for. Here's a little example that you have a question. Does entanglement actually work in a quantum computer? We'll talk about that more in the week, and you'll see that more in like people's specific examples. It'll make more sense. And also,
So usually most quantum algorithms, I would say, work by so you use superposition to kind of explore like a large space of possible answers to whatever question you're asking. That includes correct answers as well as many more incorrect ones. And then through entanglement, you kind of have this correlation where, like say, again, if you have two pennies, you can have heads, tails, tails. Say some of those correspond to right answers, some of those correspond to wrong answers. If you have like entanglement, you can only have, say heads, or tails, or maybe only heads, tails. So you can kind of, like you can, if you're clever with how you entangle it, basically, you can adjust your superposition states to only the correct answers. and not cover the incorrect answers. And then when you measure at the end, then you're much more likely to actually measure the correct answer.
Yeah, as you'll learn more, we'll talk about gates and basically, so when I talked about that circuit in that diagram on your computer, you're going to send like those commands for the microwave pulses. You could put gates there, and those are like the commands. Those are the instructions. You're telling it what to do. And like some gates can actually put the qubit in superposition, and some gates can help control like the entanglement. So it's almost like chess pieces you're using to try to get a certain outcome. So like as you move on throughout the week, you'll see more specific examples of that. I do know if you're struggling conceptually with like entanglement and superposition, I think Jesse will touch on it tomorrow. But I did optics, quantum optics this summer in my research. And I actually have like a 10-minute presentation where I go over like an interferometer for superposition and like spontaneous paramic down conversion for entanglement, which basically you take a photon and it splits, so you get two entangled photons. And because it's like conservation of angular momentum happens, they're going to be split with like half the frequency that they originally had. And if you measure one and you know it's spin up, you know the other one's spin down because they were like basically split. So like you can use that to your advantage for experiments. Like you can use one as it's called heralding. So this is like lasers. This is optical quantum computing, which is like another branch of quantum computing. We won't bore you too much with those details, but this is what I know for advantages. So like you basically take one and it's called heralding, which is like you basically grab one half of the entangled pair and measure it because now you're going to know what the other one's supposed to be, and you can do some type of experiment on it, and then you can analyze the results of what you get with what you know you should be getting because you basically know what you're sending in there because of this entanglement. If that makes, I can link my presentation too, like in the Discord, if you want to watch more on that, or we talk about that more later. But we'll talk a lot more about that throughout this week, I believe. Any other questions? Okay, back to what we have up here. This is kind of what Brian used as his example. So he's just kind of talking about like near and far as terms of kind of like the development roadmap of where we are with quantum computing. So like right now we're early. Like if you know the history of normal computing, we're around the ENIAC stages before we got to real computers that you see today. So you take this old phone, and that's kind of where we are with quantum computers today. We're just trying to do simple things. We're trying to do very simple algorithms. But decades down the road, we're going to be able to do amazing things, how the iPhone can do over the original phone. Like we're talking about here. Here's the developmental roadmap. And IBM has already talked about its plans for the near term, which include creating more reliable devices that have thousands of qubits while also making the software more approachable. This near-term hardware future is what we think will allow scientists to model that caffeine molecule that I mentioned earlier. But you might be asking yourself, what else can these expensive computers do? And one of the most famous examples is breaking encryption. You may have heard of Shor's algorithm, or people saying, once we have a quantum computer, the internet will break. And that is because of how encryption works. So basically, encryption is the tool that we use to lock our sensitive information on the internet. And so a quick sidebar on how encryption works is encryption uses really big numbers to hide your information, and it creates a special key based on a huge number and locks your information away. Only you or someone whose device that has a key is able to read your information. To be clear, a classical computer can find that key and look at your secrets, but it would take a long time for that computer to do that. For example, thousands of years on average to crack any of the keys. By that time, your iMessage probably doesn't matter that much. But quantum computers, however, have the potential to crack this type of encryption in a matter of hours. A very smart man named Peter Shor looked at the potential of quantum computers and came up with an algorithm focused on factoring those gigantic numbers, which is how you find the secret key. And using a perfect quantum computer, you could break this encryption key before you guys are having dinner tonight. But good news is we're a while away from that. But I'm going to expand on this a little bit. So it's kind of like prime factorization. So one way you can think of this, this one's kind of the most famous example. So you can almost think of like you have a lock and like a padlock, and you need like two things to open the lock. And so let's say the lock says 21 on it. That's all you can see. And you could look that up on the internet. You could see the big number, and it'll be 21. And you're like, okay, what's the password to 21? The factors of 21 are 7 and 3. But 7 and 3 have no other factors because they're prime numbers. So the two prime numbers together give you the 21. So your keys are 7 and 3. But what they do is have prime numbers like the size of a dictionary long, super huge numbers, and they multiply those together, and then you get an even bigger number, and those are your locks. So to find those factors, the only way you can do it is guess and check. So where that normal computer is like, okay, does 1 go in, does 2 go in, does 3 go in, does 4 go in, and it has to do every single one of those processes. And this is where superposition comes into play because it can check all of them at the same time with the right algorithm. So that's basically showing you the example of that nature effect that we talked about earlier of quantum computers being exponentially more powerful. Chemistry can be described both as a near-term and far-term goal of quantum computing. Scientists already have real-world results from some chemistry research that was enabled by IBM's quantum hardware. In the future, the hope is to use this type of computing to understand nature in a much more powerful way. As mentioned earlier, we think that fully modeling a caffeine molecule is in the near term. Fully modeling something like a piece of your DNA or other large molecules is more of a far-term goal. And another thing that was mentioned in my summer research with Argonne National Lab, what they were talking about for quantum computing is a big focus on like climate change, or some of the situations they can use quantum computer simulations for is big complex problems like solving or I guess making better issues affecting climate change. And here's where one of the chemistry experiments that I was talking about that kind of had already been done in the near term from IBM, and this was on the cover of Nature magazine. And the IBM scientists used a quantum computer to simulate the molecule lithium hydride. Then 1 year after the initial findings, they were able to find a 10 times improvement in fidelity using the exact same hardware, just by finding a new error mitigation techniques and applying them in the code they used. So this would be an example of the hardware didn't get any better. They just had more experience with the coding and algorithms, and they were able to increase their results tenfold. So these are some of the things that you guys will be able to do without an actual quantum computer, just on Qiskit. And that's kind of the whole point of hackathons like this. So what if you're not interested in this big science stuff and you want something a little bit more easy, I guess? Well, there's quantum games. And one way quantum computers are being used is for games. Both educational games that use quantum computers for generations of the game assets, which is Hello Quantum, is an example. And a more cool game is basically Quantum Minecraft. It's called Qiskit Blocks. And you can play a Minecraft-esque game called Qiskit Blocks, and you learn the basics of manipulating a qubit. It features 16 challenging runes. And you see there, you got some math on the walls. Talk about making math fun. We don't need to talk about anything else. Yeah, do some Minecraft with it. And now here, you can see a simple example of what I referred to earlier as a circuit when we were talking about the input to a quantum computer. And I'm not going to go over this too much in detail. I'll leave us a couple minutes here. And basically, Adrian will come into this soon. But this is kind of what like the graphical approach or the pictorial approach of what the gates we were talking about earlier will be. And we'll explore this more in the coming days. That's all I have. Thank you.